Welcome to AI News Digest 2026-0608. Today's 10 stories. Story 1, SafeGene Reusable Adapters for Transferable Safety Alignment. Story 2, Attack Selection in Agentic AI Control Evaluations Meaningfully Decreases Safety. Story 3, Position, Don't Just Fix It in Post. A Science of AI Must Study Training Dynamics. Story 4, Lean 4 Agent, Formal Modeling and Verification for Agent Workflow and Trajectory. Story 5, OpenSkill, Open World Self-Evolution for LLM Agents. Story 6, AdMem, Advanced Memory for Task-Solving Agents. Story 7, AEGIS, a Backup Reflex for Physical AI. Story 8, a Geometric Account of Activation Steering through Angle-Norm Decomposition. Story 9, Detecting and Mitigating Bias by Treating Fairness as a Symmetry Operation. Story 10, CrowdMath, a Dataset of crowdsourced mathematical research discussions. Story 1, SafeGene, Reusable Adapters for Transferable Safety Alignment. Researchers from MIT and the University of Massachusetts Lowell have released CrowdMath, a new dataset designed to expose a fundamental gap in how we evaluate artificial intelligence on mathematical reasoning tasks. The dataset contains 164 expert-annotated discussion chains drawn from the MIT PRIMES and Art of Problem-Solving CrowdMath program, which ran from 2016 to 2025. What makes this dataset special is its source material. Real collaborative research forums where mathematicians work together on open problems, with discussions that ultimately contributed to peer-reviewed publications. Here's the core problem CrowdMath is trying to solve. Most existing AI math benchmarks test models on well-defined problems with clear answers or step-by-step proofs. But real mathematical research doesn't work that way. It's messy, iterative, and social. Participants propose partial arguments, others identify flaws, someone repairs the reasoning, and gradually the group converges on a valid proof. No current benchmark captures that process, until now. The results from benchmarking 6 frontier language models are striking and a little unsettling. On the task of predicting what comes next in a mathematical discussion, the models performed quite well, achieving between 83 and 88% accuracy. That sounds impressive. But when asked to classify the functional role of individual posts, was this a proof completion, a partial step, an error, or an error correction? The best model achieved a macro F1 score of just 0.42. That's a remarkably poor result for state-of-the-art systems. What this tells us is that these models have learned the surface texture of mathematical conversation. They know what a plausible next message looks like, but they don't actually understand what's happening at the logical and epistemic level. They can't reliably tell when someone has just made a critical error versus when they've made a meaningful step forward. For anyone thinking about deploying AI as a genuine research collaborator in mathematics or other technical fields, that distinction is not minor, it's fundamental. The implications here reach beyond mathematics. If AI systems can mimic collaborative reasoning without understanding its structure, they could actually reinforce errors in research workflows rather than catch them. CrowdMath gives the research community a principled tool to start closing that gap, and its grounding in a decade of real, publication-quality mathematical collaboration makes it one of the most authentic evaluation resources the field has seen. Story 2. Attack Selection in Agentic AI Control Evaluations Meaningfully Decreases Safety. When researchers want to change how a language model behaves, making it more honest, less biased, or more focused on a particular topic, one increasingly popular technique is called activation steering. The idea is to inject a carefully chosen vector directly into the model's internal representations, nudging its behavior in a desired direction. It's a powerful tool, but until now, researchers have had limited understanding of the precise geometric mechanics that make it work. A new paper from Georgiy Aperin and Tatyana Gaintseva, submitted to arXiv in June 2026, changes that by providing a rigorous geometric account of what activation steering actually does inside a language model. Their key insight is to decompose every steering intervention into 2 separate components. The angular part, which changes the direction a token's internal representation points in the model's high-dimensional space, and the radial part, which changes its magnitude or norm. Studying 7 different language models, the authors find that concepts, things like sentiment, topics, or factual associations, are encoded primarily in the angular structure of these internal representations. That finding validates the intuition behind spherical steering methods, which operate directly on the directional component of representations. However, the researchers also find something that challenges a common assumption: norm still matters. Even though norm doesn't primarily encode concept information, it significantly affects the stability and downstream effects of steering interventions. This has a practical consequence that many researchers may have overlooked. Two different steering methods might produce the same conceptual effect, say, both successfully reducing a model's tendency toward a particular harmful output, while having very different impacts on the model's broader behavior, simply because they disturb the norm of internal representations differently. The authors argue that activation steering should be rethought. Rather than specifying a single additive coefficient that entangles both angular and norm effects, researchers should parameterize interventions explicitly by their angular and radial components separately. This would make steering more interpretable, more predictable, and more controllable. For the growing community using activation steering as a safety tool, trying to suppress harmful behaviors or reinforce alignment in deployed models, this geometric framework is a valuable corrective. It suggests that current safety evaluations may be missing important side effects, and that a more principled approach to designing interventions is both possible and necessary. Story 3, Position, Don't Just Fix It in Post. A Science of AI Must Study Training Dynamics. One of the most persistent and consequential problems in artificial intelligence is bias, the tendency of machine learning systems to treat people differently based on attributes like race, gender, or age in ways that are unfair and often illegal. A new paper by researcher Nishit Singh, submitted to arXiv in June 2026, proposes a fresh mathematical approach to this old problem, drawing on a concept from physics and mathematics: symmetry. The core idea is elegant. In physics, symmetry means that a system's behavior doesn't change under certain transformations. Rotate a perfect sphere, and it looks the same. Singh applies this logic to fairness. A classifier is fair if its output doesn't change when you switch a person's sensitive attribute, say, changing their listed gender or race, while keeping all their merit-related features exactly the same. If the model's decision changes when only the sensitive attribute changes, that's symmetry breaking, and symmetry breaking in this framework is bias. From there, the approach uses a technique called loss-based regularization to penalize the model whenever it breaks this symmetry, effectively training it to restore fairness as a mathematical property. Tested on 4 synthetic datasets with varying levels of noise, correlation, and built-in bias, the framework achieved over 90% reduction in fairness violations, with an accuracy cost of only around 5%. What makes this approach particularly useful is what it doesn't require. It doesn't need knowledge of a causal graph, the complex diagram of cause and effect relationships between variables that many fairness methods depend on. It's also computationally lightweight, and it generalizes to any sensitive attribute that can be defined as a simple flip, making it applicable to forms of discrimination that standard benchmarks don't even cover, like regional or cultural biases. The main caveat is that all testing was done on synthetic data. Real-world datasets are messier. Merit features and sensitive attributes are often entangled in ways that are hard to cleanly separate. Whether this elegant framework holds up against data like criminal recidivism scores or loan applications remains to be seen. But as a theoretical foundation and a practical starting point, the symmetry-based approach offers a genuinely novel and promising direction for building fairer AI systems. Story 4, Lean 4 Agent. Formal modeling and verification for agent workflow and trajectory. Lean 4 Agent proposes using the Lean 4 formal verification language to specify, verify, and debug LLM agent workflows and execution trajectories. This addresses a key gap in agentic AI. Most systems lack rigorous methods to ensure correctness in multi-step tasks. The approach mirrors formal methods used in mathematics and software verification, bringing new rigor to AI agent reliability. Story 5, OpenSkill, Open World Self-Evolution for LLM Agents. OpenSkill studies the problem of self-evolving LLM agents in open-world settings where no curated skills, successful trajectories, or verifier signals are available, only a task prompt. The framework enables agents to build skills and verification signals from scratch using open-world resources. This represents a significant step toward truly autonomous, self-improving AI agents. Story 6, AdMem, Advanced Memory for Task-Solving Agents. AdMem introduces a unified memory architecture for LLM-based tool-using agents, specifically targeting long-horizon tasks that require remembering, organizing, and reusing knowledge across interactions. Unlike prior work that stores only factual or procedural successes, AdMem also handles failure cases and scales online. This is a practical contribution to making LLM agents more capable in real-world deployments. Story 7, AEGIS, a backup reflex for physical AI. AEGIS introduces a safety mechanism for robot manipulation policies that detects high-risk steps before failure occurs and selectively escalates to a stronger policy. It uses lightweight probes on weak policies, frozen activations, to identify when the robot is likely to enter an unrecoverable state. This is a practical contribution to physical AI safety and reliable robot deployment. Story 8, a geometric account of activation steering through Angle-Norm Decomposition. This paper revisits assumptions underlying linear and spherical activation steering methods for controlling language model behavior. Through controlled empirical study, the authors analyze the role of hidden state norm versus direction in carrying concept-relevant information. The findings refine the theoretical foundation for activation steering, a key tool in LLM interpretability and control. Story 9, detecting and mitigating bias by treating fairness as a symmetry operation. This paper formalizes ML bias as a symmetry-breaking operation, defining fairness as invariance of classifier outputs under counterfactual switching of sensitive attributes. Loss-based regularization is proposed as a symmetry-restoring mechanism and evaluated on synthetic datasets. The formal framework offers a principled approach to fairness in high-stakes ML deployments. Story 10, CrowdMath, a dataset of crowdsourced mathematical research discussions. CrowdMath introduces a new benchmark dataset capturing collaborative, open-ended mathematical problem-solving discussions, filling a gap left by existing benchmarks that only evaluate well-specified problems with final answers. The dataset includes partial arguments, error identification, reasoning repair, and incremental synthesis. This is relevant for evaluating LLM reasoning capabilities in more realistic, collaborative settings.